Hi, I'm Ridley.
I'm Michael.
And I'm John, and this is Lab 6, Stress Optic Coefficient and Faraday Rotation. So here's our Faraday rotator setup. We have two different materials that we're going to be using for this. This is our water cavity, and this is our glass rod. So these each have a different Verde constant, which means that when they go through this Faraday cavity, they will actually be displaced angularly by different amounts based on the current running through this coil, which will induce a stronger or weaker magnetic field, thus causing a greater rotation in the polarization. So this is related to prior knowledge. We learned about Verde constants and dextra and levorotatory materials while we were in our photonics and lasers class. So this actually relates pretty much directly to that, showing how those materials react in the presence of a magnetic field. So the Faraday rotator is important as an optical component because it allows you to optically isolate systems. There are some systems where having back reflections in the system can actually destabilize your laser beam or break it. So in those cases, you need an optical isolating system in order to prevent those systems from being damaged.
So some of our significant results for the Faraday rotator was to calculate the Verde constant of both the glass tube and the water tube. So we take our theta equals VBL equation and plug in what we know the magnetic field is. And since we created a graph of theta versus current, we know our slope would be V mu naught NL, and dividing by mu naught NL we can get the Verde constant. Plugging in all of our known values and using the slopes we found from our graphs, we get these values for the Verde constants. You can see that they vary a lot from the two different methods. So we can assume that the maximum extinction method is going to give us our best results. However, because magnetic field varies radially, if the beam is not going directly through the center, we will get some source of error.
For this part of the lab, we looked at the stress optic coefficient for a material. And what this is that for when we apply a certain stress to the material, it adds a birefringence to it. What a birefringence is the difference in refractive index based on the different directions through the material. So what this results in is that the different polarization states of light will travel at different speeds, which causes this material to act as a retarder. So the amount of retardance that this material has for any given stress is determined by the stress optic coefficient, which we calculated. We have learned about birefringence in Cole's 6th class for physical optics, but the only difference in this case is that this material, we're applying a stress to cause it to become birefringent, when previously the materials were naturally birefringent.
To calculate the stress optic coefficient, we used the half-wave measurement method and plugged in all of our known and measured values to get a stress optic coefficient of 5.26 times 10 to the negative 12 inverse Newton meter squared.
So this is our Faraday rotator setup. I really like this setup because it actually it demonstrates really well this concept that we were talking about, and it shows how this is actually a different value for these different materials.
So the part that we didn't like was the stress optic part because when we were recording data points, the values kept fluctuating, so we couldn't get reliable measurements.